All right, so we're going to go over the capacitance notebook for now. Sorry, it took me a little bit to get this up there. I wasn't finding great videos that covered exactly what I wanted and corresponded to the examples that we have here. So, life gets in the way, but better late than never. I know some of the stuff on the front page is a little bit out of order from what we did in class. So, it's fine if your first page is different than mine. Just make sure that you get all this stuff on your first page. One thing we didn't do in class, and we did look over the standards over here, but one thing we didn't do was go over relevant equations that are on the equation sheet, the official equation sheet. So, definition of capacitance. C defined to be Q over delta V. Absolute value, capacitance always positive. For a parallel plate capacitor, the capacitance is K epsilon naught A over D. We will derive that, and we'll talk about what K means. That's a dielectric. It's related to a dielectric that you could insert between the capacitor plates, which changes the capacitance. So if you have nothing stuck between the plates, then the capacitance, this would be a 1, and the capacitance would just be epsilon naught A over D. Equivalent capacitance in parallel is the sum of the individual capacitance. Equivalent capacitance in series is the sum of 1 over the individual capacitances. So this would be 1 over C1 plus 1 over C2 plus 1 over C3, etc. There are 3 different ways of writing the energy stored in a capacitor. This is U for potential energy, the potential energy in a capacitor. And we will derive these. But basically, all 3 of these involve substituting C equals Q over V in various forms. Take this first one, 1/2 CV squared. If you substitute in for C, Q over delta V, you're going to get Q, and a delta V on the bottom cancels with a delta V on the top. And that's how we get this, 1/2 QV. And then if you substitute in here, delta V, if you rearrange this, delta V would be Q over C. And when you substitute Q over C right here, Q times Q is Q squared over C. So all 3 of these can be found by taking any one of them and doing some substitutions. Last thing to be aware of, this is not on the equation sheet, but the last thing you want to be aware of is capacitance is a physical property and can only be altered by changing a physical characteristic, like the size of a capacitor, the shape of it, or the dielectric that you have inside of it. You cannot change the capacitance by changing the charge or the voltage. If you stuff more charge onto a capacitor, that will have the effect of changing the voltage, and those changes will cancel each other out. If Q goes up, V goes up, and the ratio of Q to V stays the same. We can see that here, that capacitance is K, which is a property of the dielectric. That's what a material that you would stick inside, an insulating material. A is the area, and D is the distance between the plates. So physical property, physical property, physical property. Any equation that you come up with for capacitance, for any type of capacitor, whether it's spherical, cylindrical, or parallel plates, what you get should only have, like in the long run, can or should be able to be reduced to only physical properties. What we did look at in class was a parallel plate capacitor, and we said that we have a positive plate and a negative plate, plus Q minus Q. The positive plate has an electric field which points away. The negative plate has an electric field which points towards. And these electric fields, from a Gauss law for infinite sheet, it was sigma over 2 epsilon naught. This does not have D in it, which tells us that the field is constant. It doesn't matter how far off the plate we are. So up here, the field is the same as here, is the same as here for the positive plate, and same for the negative. Because the fields go in opposite directions outside the plates, they cancel out. The fields go in the same direction in between the plates, so they add together. So when you do 2 times this individual electric field, you get just sigma over epsilon naught. And sigma, if you were dealing with, plates of a certain area, and we can model plates of a certain area as infinite sheets as long as the 2 plates are close together. Sigma would be the charge per unit area, Q over A. So that's the first page. I think most of you have that, but for those that weren't in class, there it is. There were several different forms for capacitors. Dielectric is in the middle here. That's just an insulating material that you put in the middle. We'll talk about why you would want to do that later on. Cylindrical capacitor is 2 concentric cylinders. A spiraled capacitor is really a parallel plate capacitor that's been rolled up into what looks like a cylinder. But this is really a parallel plate capacitor that has been rolled up to save space. And a variable capacitor, these fins will move in or out, which will change the amount of area that overlaps. And by changing the amount of area that overlaps, you will effectively change the capacitance. So this is a variable capacitor. It could be used for tuning purposes. Capacitors have certain properties in AC circuits where having a tunable capacitor is a desirable thing. Definition of capacitance was C equals Q over delta V. Absolute value capacitance is always positive. So it doesn't matter if you use Q as positive or negative, delta V as positive or negative. The Q here refers to the charge on a single plate. The plates will have equal and opposite charges. So the net charge on the capacitor will be 0. But this is the charge of a single plate. The unit of capacitance is the farad, named after Michael Faraday. We'll study Faraday's law when we get to magnetism. A farad is a coulomb per volt. That's charge over volts, right? Q over V. We did an example in class where we looked at just a sphere, one single sphere, and what would its capacitance be? How big of a sphere would you need to have these various capacitances? Notice that the expression we got for capacitance here, 4 pi epsilon naught, those are all constants, and R is a physical property. That's the radius of the sphere. And capacitance only depends on physical properties. We found that to get a 1 farad capacitance, you need an incredibly large metal sphere. That's why you don't see capacitors that are just single metal spheres. It's a very ineffective design. So let's take a look at a parallel plate capacitor in more detail. First thing I want to do is run through Gauss's law here. You can use Gauss's law. You got to remember, there's a couple ways of doing it. You could use Gauss's law for one plate and double the result, which we did at the first page. Or you can remember that there is no electric field outside of the capacitor. So there will be no flux through the top end cap and no flux through the lateral surface area because the electric field is parallel. The only flux will be through the bottom. So when you go to do Gauss's law here, we have surface integral of E dot dA. Electric field is constant. dA just becomes pi r squared, not 2 pi r squared because only one end cap had flux. The charge enclosed is sigma times pi r squared, right? Charge per unit area times area over epsilon naught. The pi r squareds cancel, and you see the electric field is sigma over epsilon naught, which is double the result that you get from just one slab of infinite charge, because here the fields in the middle have added together. If we want to find out the capacitance, we need to find the voltage. Delta V is ED in magnitude. So E was sigma over epsilon naught times D, and sigma is Q over A. And by taking that result and doing Q over V, which is the definition of capacitance, the Q's cancel, flip the rest of this stuff around, we get epsilon naught A over D. Again, the capacitance of a parallel plate capacitor only depends on the area and the distance between the plates. This is an example that does not have a dielectric inserted into this open space here. For a cylindrical capacitor, now if you can't read your printout, this was the height of the capacitor, L. We had charge negative Q on the outside, charge positive Q on the inside. The inner radius is A, and to the inside of this outer shell is B. And I'm not going to go through it, but Gauss's law gives Q over 2 pi RL epsilon naught for the electric field in this empty region here. So if we want to find the voltage difference between this surface and this surface, the delta V, we need to integrate the electric field from A to B or from B to A. It doesn't matter which way you do the integral because we're only interested in the magnitude of delta V, not whether it's necessarily positive or negative. So again, you can see our electric field over here. We're going to do the negative integral from A to B. That's because the negative there is to represent the work that an external source would have to do, and they are fighting the electric field. The electric field does negative of the work that an external source would do. But again, this negative is not going to be important because we're only looking for magnitude. I'm just trying to tie up all the technical ends here. So we're integrating basically 1 over R dr. Integral of 1 over R becomes ln. And then we evaluate this. We'll get the ln of B over A. Now, I did not use any more absolute values around here, but B is bigger than A, right? B was the outer radius, A was the inner radius. When you do the ln of B over A and the top number is bigger, you will get a positive. If you flipped these around, in other words, if we had done our integral backwards, instead of from A to B, if we went from B to A, this would be the ln of A over B, and the ln of A over B would be negative if A is smaller, right? The ln of 1/2 is negative. The ln of 2 over 1 is positive. So if you plug numbers in here and get a negative, just make it positive because the delta V needs to be positive. So now we do Q over delta V. Q over delta V that we just got, we get the expression for capacitance of a cylindrical capacitor. Look at everything in here. Number, L, physical property, epsilon naught, number, B and A, physical property. So the only variables here are L, B, and A, and those were the dimensions, the size and shape of our capacitor. Again, capacitance is purely a property of the physical characteristics of your capacitor. So there is something called equivalent capacitance. The idea behind equivalent capacitance is if you had multiple capacitors hooked up in some kind of arrangement, what single capacitor could you use that would act the same? In other words, can you take two individual capacitors that are hooked up in various ways and find a way of replacing them with one capacitor that, if you replaced it, the circuit would behave exactly the same? The same amount of energy would be stored, the same charge would be stored, everything would act kind of the same. Now, in a, and we call this a parallel circuit, because they're next to each other, they're kind of in parallel. A parallel circuit, you have branches. I can go this way to get back to the voltage, or I can take this lower path to get back. If you have options of which way to go, That's an indicator of a parallel arrangement. In a series arrangement, which we'll look at next, the capacitors would be connected one after the other, and you would have to go through all of them. You would not have a branch. There would be no options of how to go around the circuit. So you can identify parallel circuits by whether or not you have a split, and you can go through one or the other. So when these capacitors here are both hooked up to the battery, and notice I can go from this side of C1 to the battery, and the battery goes right to this side of C2. So this, and all of these are all metal. Anything that's metal and is in equilibrium is going to be equipotential. It's going to have the same voltage. So the voltage across C1 is the same as the voltage across the battery because C1 is connected, both sides of it, directly to the battery. So is C2 connected directly to the battery. So the voltage across C1 and the voltage across C2 are going to be the same. There's no reason to think that C1 and C2 must be the same. They might be the same, but they don't have to be. And if C1 and C2 are different, Q1 and Q2 will also be different. Now, the total amount of charge stored on both of these, like let's say this right plate and this right plate, the total amount of charge stored there is going to be Q1 plus Q2. If we apply the definition of capacitance, which was C equals Q over V, and you rearrange that, Q equals CV. So Q1 is C1V. I don't need to put V1 because there's only one voltage in this problem, right? Voltage of the battery is V1 is V2. So CV and C2V, C1V, C2V. Now I can take that voltage and factor it out, and I get Q total equals C equivalent times voltage. Notice that if I divide by the voltage over here, I get C equals Q over V, which is the definition. And the equivalent capacitance is C1 plus C2. So for capacitors in series, it's pretty easy to find the equivalent capacitance. You just add them up. If you had a third capacitor up here, like if there was another branch that went up here, then you would have C1 plus C2 plus C3, etc. On the equation sheet, that's written out with summation notation. For capacitors that are in series, this is an example of series. You start at the battery. You have to go through both of them. There are no branches in this circuit. To go around, you have to go through both of them in a row. They are in series, one after the other. Now, these two capacitors do not have the same voltage, or they don't have to. They might if they were equal, but that's a special case. They're not both connected directly to the battery. What is true is that they will have the same amounts of charge. If the battery spits out one electron, it's going to pull in one electron on the positive side. For every electron that gets pushed out, an electron gets pulled in. So this charge here has to be equal and opposite to this charge over here. Take a look at these plates in the middle. This is a gap of air. This is a gap of air. This is really a break in the circuit. And if you start with uncharged capacitors, then this middle section has no charge to begin with, and it will have no charge to end with. Now, if you get minus Q over here, by symmetry, you're going to have plus Q. If this is plus Q, this one's going to be minus Q in symmetry to that. So what is true about capacitors in series is that the charge stored on each plate in magnitude must be the same as the other charges. The voltages can be different, the capacitances can be different, but the charge stored on each plate in magnitude must be the same. And for these battery symbols, you can tell a battery or a voltage source because one line is short and one line is long, and the line that's long is always the positive side of the battery. The line that's short is always the negative side. So capacitors are not always equal. They might be, but they don't have to be. the voltages are not always equal. The voltages would only be equal if the capacitors were. If you took two capacitors that were the same value, like 1 farad and 1 farad, then each of them will get half of the battery's voltage. But that's a special case. So the voltages are not always going to be equal. But what is true is that the magnitude of charge on each plate is always equal. Q1 will equal Q2. So the voltages here, if you're going to start, let's call the negative side of this battery 0 volts. And this side of the battery is at 9 volts. If I go around the circuit, I'm going to jump some voltage here, and I'm going to jump some voltage here. But what I do know is that this side is going to be at 0 volts because it's connected straight to the battery. This side is going to be at 9 volts since it's connected straight to the battery. So to go from the far left to the far right is going to equal the voltage of the battery. And that's also going to equal V1 plus V2. So that's what we start with here. Voltage across the battery is V1 plus V2. C is Q over V, or if you rearrange that, V is Q over C. Oh, and I forgot my, I don't need to put a 1 and a 2 here on the Q's, because remember, the Q's are the same. I can factor out I can factor out the Q's. When I factor out the Q's, that leaves me 1 over C1 plus 1 over C2, and that is 1 over C equivalent. Why is this C equivalent on the bottom here? Because think about rearranging this. If I move this over and bring the V battery down, I get CEQ equals, I can write this out again. Here we would get CEQ equals Q over V battery. That's, again, going back to the definition of capacitance. C equals Q over V. So 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3, etc. So capacitors in series follow a 1 over law. Capacitors in parallel follow just a straight up summation. We are going to skip over the next few examples and go over the energy stored in a capacitor. One way that you can imagine charging a capacitor is starting with 2 parallel plates and moving negative charges one at a time from one plate to the other. In reality, charges would flow off the plate into the battery, and other charges would flow from the battery to the opposite plate. But really, all that is taking a different path to get from point A to point B. And we know that the work done against an electric field is independent of path. Just like gravity, it only depends on the difference in height between the starting and the ending, not on the path that you take to get there. So if you have 3 ramps with different shapes, but they're all the same height, and you let mass slide down these frictionless ramps, the mass will always have the same speed when it gets to the bottom. It might take longer to get to the bottom in one case than the other, but will always have the same speed representing the same amount of energy. Same thing here. The energy is independent of path. So even though this isn't the path that the charges take, for the purposes of calculating energy, it doesn't matter because energy is independent of path. So pick the path that's easiest to calculate. If you started with a negative charge here and you moved it up to the other plate, that would be very easy because neither plate is charged and you're not fighting an electric field. But as soon as one plate begins to get a negative charge and the other plate begins to become positive, you're going to have an electric field here. And the next time you go to move a charge up, you're going to be fighting the electric field. And the next time after that, you're fighting an even bigger electric field. The more charges accumulate on the top plate, the bigger the electric field gets, and the harder it's going to be to force one more charge up to that top plate. So when we look at the amount of work that's done, right, energy would equal QV. The energy is the amount of work done by an external source to move from A to B. So work is the same thing as energy. If energy is QV, work is also QV. In this case, we're looking at the tiny amount of work done to move a tiny charge through some voltage. And the voltage here is Q over C. That's just the definition of capacitance rearranged. Q is not a constant, right? It's changing as we add more charges on there. So when we integrate, we're going to integrate, it takes zero work at the beginning to some final amount of work. And we start off with no charge, and we're adding some total amount of charge Q to each plate. We're separating the charges in essence. And when you evaluate this, right, the integral of Q dQ is Q squared over 2. Now you can see where the 1/2 is coming from in that formula. The net work that's done to separate or move the charges is Q squared over 2C. And the work that you do to separate the charges as an external source is stored up as potential energy in the electric field that was created. And we have 3 variations to this formula again. The one we got from our integral was Q squared over 2C, or 1/2 Q squared over C. C is Q over V. If you put a Q over V on the bottom of this, it would flip around. One of the Q's would cancel, and we'd get QV over 2. And Q is C times V. So if you plug in CV here, you get C times V times V, CV squared over 2. All 3 of these equivalent. That's going to be all that we'll cover for now. We'll go over some more of this in class, and we'll see you then.